Hi everyone. Um, this video I'll be talking about different ways of measuring the amount of water in the soil, and we need that to be able to irrigate effectively. So the first method is the feel method, um, and this is a very basic method, but it only requires experience. So what happens is the producer or the farmer drills a hole in the soil, and then he takes out that soil and puts it in his hand, and then he just feels the amount of water. So what he thinks the amount of water in the soil is. And here's just a picture of a grondboer or auger, and so you can see that part he drills into the soil. So if this is the soil surface, he drills that into the soil, and when you extract that thing, the soil is still stuck in that area in the container, and you put that in your hand, and then a table like this will be used to determine the amount of water in the soil. Next up, we've got the gravimetric method. So that's similar, just in the fact that the producer again drills a hole in the soil like this, and then he extracts that amount of soil, and then he takes it to a lab or to a room where he places it in something similar to an oven. And well, before that, he measures the soil, then he places it in an oven that dries it, so all the water that was in the soil is lost, and then he weighs it again, and then that difference in weight is the amount of water that was in the soil. And so the advantages of this method is it's very cheap, it's objective, it's very accurate, and the salt content in the water doesn't influence the measuring. The disadvantages is that it's very time consuming, and it requires the right equipment. But because it's so time consuming and you only find out the amount of water the following day, it's not very effective if you want to use it for irrigation, and it's also a destructive method. So once you've extracted that soil, you can't use that same area again. So next up is electrical resistance. This is another method used to calculate the amount of water in the soil. Firstly, it should be noted that water has a current due to impurities such as salts and ions. So if you want to put an electric current through water, you can do that. So what happens with this device is that you are measuring the electrical resistance in the soil, and the amount of water in the soil can then be determined because you measured the amount of electrical resistance. So how this looks is you've got say this is your soil surface again, and then you've got a porous gypsum block, so this thing. Then you've got two electrodes, so that's one electrode, and this is another electrode. So because there's a lot of pores in this gypsum block, water moves into the block from the outside. So water moves in, and water is between these two electrodes. So then what happens is the electrical resistance is measured, and because the electrical resistance is known, that is then used to determine the amount of water in the soil. So that electrical resistance is gives you an indication of the amount of water in the soil. And so the advantages is that it's cheap, non-destructive to the soil, so you can still measure that exact same amount of or that same area the following day. The disadvantages is you have to calibrate each individual block according to the size of the block and the percentage of dissolved salts in the soil solution. So every time you put one of these gypsum blocks into the soil, it needs to be calibrated characteristics such as dissolved salts can influence the measurement, and that is because salts play a big role in the current and then short lifetime. So if you have one of these gypsum blocks for too long, it becomes ineffective. Okay, so next is the neutron probe, or the neutron water meter. So how this probe looks is that it has two main areas, if I can call it that. So you've got your probe and it's in the soil, so that's your soil surface, and then it's got a source, so you can put that as source, and then you've also got your detector. So what happens is your source sends out a lot of neutrons, so the neutrons get sent out and it binds to your hydrogen molecules. And so we all know water is hydrogen and oxygen, and as soon as your neutrons bond to these hydrogen atoms, the rate at which it moves slows down. And so you have a detector, and this detector measures the rate at which your hydrogen atoms or neutrons in the soil moves, and it then detects how many atoms or neutrons are moving at that slow rate, and then this gets related back to the amount of water in the soil. So here's a picture, and so you can see there's a source and then there's a detector, and so it just measures the movement of neutrons. So again, fast neutrons collide with hydrogen atoms. The slower neutrons is then detected. The depth of the reading is logged as the source is lowered. So as the source is lowered into the profile, it then measures for the whole profile. And then something to note is just this part, the radius of influence varies. So in drier soils, the area that you can measure, the radius is a lot bigger than in wet soils, and you can only measure deeper than 300 millimeters into the soil. Okay, so then the advantages: quick and easy, can be taken repeatedly so you don't harm the soil, it's non-destructive, measurements can be taken at various depths except for near the soil surface, and it's accurate. The disadvantages is possible radiation, so it's possible to get sick, and then you can't measure near the top. Specialist calibration, and no continuous logging of data, and then most expensive device. Next up, tensiometers. So this device doesn't measure the amount of water in the soil, but it measures the matrix potential, which we then convert into the amount of soil or amount of water. So just to remember from soil science, what matrix potential means is it's basically how tightly your water molecules, how tightly they bond to your soil particles. So if they bond tightly to your soil particles, it's a lot harder for plants or plant roots to take up this water. So if we look at the composition, you've got a ceramic tip, a tube, and a vacuum meter. So here's a indication of how it looks. So it's your tube, and at the end you've got that ceramic tip, and then you've got a vacuum at the top. So what happens is you fill this thing up with water, and then a vacuum is created at the top. So then this will be water, and if you place this into the soil, the water starts moving out of the tip, but because you've created a vacuum, it's not easy for this water to move out of the tip. So there's a tension that's created between the soil surrounding the potentiometer and the water that's in the ceramic tip. And so when the soil moisture level decreases, soil withdraws water from the meter. So if the soil is dry, water will move out of the potentiometer. And when the soil moisture increases, so when there's a lot of water in the soil, the water will push back up into the potentiometer. And so basically this tension at the top where the air is constantly measured. So when water flows out of the potentiometer, there's a lot of tension at the top, and that's measured. And when the soil is wet and water pushes back in, then the potentiometer at the top is also influenced by the water pushing up. So yeah, that is how a potentiometer works. And so you'll find sometimes that a couple of them are placed next to each other at various depths. And so the advantages is it's cheap, readily available, and continuous data logging. But the disadvantages is this ceramic tip can break very easily. So oftentimes you'll get a faulty reading and you won't realize that the tip has broken off. Limited to a suction of 80 kilopascals. So in extremely dry soil, it could break. So what happens is this vacuum is disturbed and all the water flows out. So regular maintenance is important. And then the last one is capacitance measuring. So as I said earlier with the neutron water meter, soil has a specific dielectric constant. So if I can explain this. So in a circuit, electrical circuit, you've got a capacitor. And so current moves in this direction. And here is a substance, a material that doesn't really conduct any electricity. And so various different materials have different values as their dielectric constant. And so what happens is in soil, this kind of circuit is built, except that with something like the Diviner 2000, what you'll see is that a couple of electrodes are placed in a row. So you'll maybe see something like this. And then what happens is an extremely high current will flow through the electrodes. And then the current at the end is measured. So because we know what the dielectric constant of water and soil is, so in the spaces between the electrodes, here's a picture of how that would look. Because we know what this value should be for different kinds of materials, we can actually then determine the amount of water around these electrodes. So the working is a sensor sends high frequency pulses into the soil and evaluates the difference between the soil air mixtures by dielectric properties. Okay, so you insert this electronic probe into the soil and it will give you readings for the soil as a dielectric constant, which you can then convert over into the amount of water. Okay, and the advantages is it's non-destructive, so you can use the same area again. It measures the volume of water as opposed to potentiometer that only measures the matrix potential. It's very accurate, and then the disadvantages, it's expensive. The salt content can influence the measurement, and as well the electrodes must make contact with the soil. So what happens if it doesn't make contact is air also has a value for dielectric constant. So you are putting this electrode into the soil, and here's your soil particles. And so if there's a big difference just a big difference, if it's far away from the soil particles, it will measure the air as a dielectric constant, and your value will be incorrect. And that is it for this video.